Hello everyone and welcome back to a new video, and today's video is going to be a bit different. No more of that intro and outros. I think I'll rather just straight get into the content. So I'll get started with generative AI. As promised, this is a part 3, a continuation to the previous 2 AI videos that I made. And so yeah, let's start with what generative AI actually means. Now, when discussing what generative AI defines as, it's very different from discriminative AI, which is just all about predictions. Generative AI is all about generating new information, new data that you can actually use using old information. That's basically what this entire field is about. And there are 6 main types of these algorithms that generative AI can be classed as. There's also one extra one, which is number 7, but we'll get into that. So let's start with what number 1 is, which is actually variational autoencoders. In simple context, VAEs, as known as variational autoencoders, they basically have 3 distinct parts. One called an encoder, a decoder, and something in between called a latent space. And this latent space, you can think of it as a probability distribution, more of a Gaussian or normal distribution. Alright, so basically what happens is this encoder takes high image data and breaks it down and compresses it into more of a normal distribution that sets it into this latent space. Okay, and basically what happens is the decoder learns how to upsample the broken down compressed image into a newer form of image by sampling from that latent space. I know this is a bit hard to grasp conceptually, but this is how it works as an essential concept. Now, following this architecture, we have something known as generative adversarial networks, or more known as GANs. This was first introduced by Ian Goodfellow in 2014. This architecture has 2 main components, which are a generator and a discriminator. The generator learns how to produce new images that get more realistic, and this discriminator basically tries to tell the differences between which is the actual image and the generated image. This is a competition between the generator and the discriminator to tell and compete against producing images and also classifying images as fake and real as well. So yeah, this is quite an interesting architecture, and GANs are also very versatile. They can be used in image generation, they can be used in music generation. I highly recommend checking out the variations of GANs as I've listed it down in the comment section. Now, for the third algorithm, we have something called the normalizing flow model. And basically the only difference, or the only thing that this algorithm adds, is something called a coupling layer. And basically what a coupling layer has is its scaling and translation. Translation would directly relate to the changes applied to the graph in terms of mean, and scaling would directly affect the graph in terms of its variance. Alright, so we stack these many coupling layers on top of each other and compress this data into a normal distribution. What we need for normalizing flow model is it needs to be tractable, so we can reverse the function to get an inverse function, so it has an inverse density function. And the other thing is it needs a calculable Jacobian determinant, and this can be achieved through a lower triangular. Alright, but I won't go in depth into it because it's more math heavy. Now, the fourth algorithm is something known as a EBM, or an energy based model, and basically what it uses is the energy formula. So basically it's an integration and uses E and all that stuff. But the only issue is that it has an untractable function. It's untractable because it has an integral, and when we know classically, when we integrate something, we always get a C, and that C is usually unknown. So we cannot inverse this function. So to solve this problem, we actually have 2 methods, something called the Langevin dynamics and contrastive divergence. Now, the Langevin dynamics is very simple. We are going to visualize a mountain that has peaks and throws. So basically, when there's a throw, there's a higher probability because there's lower energy. And when there's a mountain, there's a peak, there's higher energy, so there's lower probability. So basically what we're going to do is we're going to calculate the gradient and then go in the negative direction of the gradient, and will stay around that area to produce images with higher quality. But you also need to add randomness so that we don't get stuck at the local minimum. Alright, and contrastive divergence is basically just a loss function. So basically we deepen the throws and we increase the crests so that we have a higher probability of landing around the area of the local minimum. So for the fifth algorithm, we have something known as the diffusion model, and this is the current state of the art tech. So diffusion models have two main compartments, mainly made up of a noising element and a denoising element. The noising element, as you know, gradually adds noise to an image until it almost becomes pure Gaussian noise. Then a U-Net, or known as a denoiser, learns how to denoise the image at each time step based on a sinusoidal embedding. And the U-Net is made up of downsampling, residual blocks, upsampling layers with skip connections. Okay, now beyond image generation, we have also the probability prediction of sequential information, and this is achieved through something called autoregressors. Autoregressors were initially made up of LSTM, long short-term memory, GRUs, and bidirectional RNNs. GRUs stand for gated recurrent units. But I'm not going to go in depth into this architecture because it's more older and has been replaced by a newer model known as transformer. No, not the car or not the Autobot.
I'm going to turn into a truck now. Birch, church, a charge. Ding, ding, church. Plug it up, plug it in. Let me plug in.
But transformer architecture. Alright, so transformers are mainly made up of feed-forward networks and also attention heads and multi-head attention. Attention heads are the core application of transformers. Attention heads are made up of queries, keys, and values. And these three basically learn the relationship between the text and the information provided by each text to predict the next word in a sequence. And this has been proven so advanced that now we have ChatGPT 5 that uses this technology, and it's been excellent at predicting newer words in a sequence. Alright guys, I'll catch you in another video, and peace. No, I'm just kidding. Alright, there's one more thing that I want to add, which is quantum AI. Quantum AI actually integrates quantum technology with artificial intelligence, and I think this is going to be a breakthrough technology in the process of achieving artificial general intelligence. And so yeah, I think that's it, and I'll catch you guys in another video.